let's say, what is a minimum phase digital filter? The definition: an LTI filter, an LTI minimum phase filter in digital domain or continuous time is that phase of this one, if we define a Z transform of that, and its inverse are both analytic in the exterior of the unit circle. For continuous time, they should be on analytic side for positive. So in other words, all the zeros and poles of L of Z, because these want to be analytic, all the poles of these one should have a real part of Si as the magnitude of Zi for the poles should be smaller than 1, but because it's inverse also that, so the zeros of these should also have. So if all poles and zeros of L of Z are inside the unit circle, and ROC includes the unit circle and Z infinity, then we call these minimum phase. For continuous time signals, instead of being inside the unit circle, they should be on the left side, and ROC should include the J omega axis. So, and also it should include a real part of S goes to infinity. Okay, so here when magnitude of Z is infinity, it should be, and so in other words, if this guy is very, very big, Z to the power minus n is 0, and this converges. Why? Because if any of these components for negative n has value, which is your filter is not causal, then this guy becomes infinity. So this is for this. So this is for causality, and the unit circle, the RC including unit circle, is for stability. So stability is the convergence around the unit circle, and causality is the convergence. So this is stability, and causality is the convergence when Z, magnitude of Z is large. So this is for discrete time signal. For continuous time signal, stability is convergence around J omega, S equal to J omega, and causality is for real part of S goes to plus infinity. So when real part of S is very large, the Laplace transform of your signal should converge in order to have causal. So for the discrete time filters, it means that L of Z and this guy, they should be stable, and all roots of L of Z and 1 over L of Z, which is gamma of Z, they are in the unit circle. They are inside the unit circle, not on the unit circle. So if they are on the unit circle, they are critically minimum phase. So the same thing for continuous time. For the continuous time, instead of unit circle, because the unit circle in discrete time is equivalent of the J omega axis for, so this is discrete time signals. So the unit circle, this is for discrete time signal, is equivalent to j omega axis. Stability means here for continuous times, but for discrete times, this is a stability when you go away from the center. And I'm sorry, causality. So let me write it here. So causality is when you go away from the center, and causality is when you go toward this direction. But stability here, stability is on this one. So for discrete time, means the convergence is on the unit circle is on your function converges, and for continuous time is on j omega axis. So that means that the Fourier transform of your signal should exist. Here, the Fourier transform should exist. If the Fourier transform exists, your filter is converging. So spectral factorization, either discrete time or continuous time, should be using minimum phase filters. So spectral factorization of a digital process is to solve this problem. So the power spectral density is given, this function is given, and then we want to, from this one, we want to find this one. So it's obvious, you get this one, find zeros and poles, and from this equation we see that every zero and pole, if zi is a zero, therefore 1 over zi which is mirror of that is also another pole, and if zi is a zero, also the inverse of it is also. So in continuous domain, if Si was a pole, you should solve it for minus Si. But for discrete time, you have to do this one. So it's kind of a little bit different. Because remember that in Z transform, when you say L of Z, you say summation of Li and then Z to the power minus I. For Laplace transform, L of S is integral. So instead of summation, you have integral, and you have L of t e to the power minus st. So the difference here is this is I. So Z is equivalent of e to the power of s. And then if you take logarithmic or exponential relationship between z and s, you see that a circle, a unit circle. So if you put e to the power of j omega becomes s, becomes z, becomes unit circle. So on the continuous time domain, the j omega axis is equivalent to circle in discrete time domain. So this is the only difference. So here we have the same thing. If you write here, this is x of n. And the same concept, we have whitening filter, innovation filter, and then same problem. So the only difference is the theorem is that if this function, because this is periodic, so the integral over one period should be fine, and they don't need to, for continuous time, you had this divided by 1 plus omega 2. Here we don't need to have that one. So if you have this one, then you have a power spectral factorization, or your random process is regular. So everything is similar, same concept and same methods, and then you could find this one. The power spectral density of the power spectrum density of the WSS can be always written a function of cosine of omega. Okay, and cosine of omega is equal to e to the power of j omega plus e to the power minus j omega. And remember that e to the power j omega is z, so e to the power minus j omega is equivalent to z. So cosine of omega is equivalent of z plus z minus 1 divided by 2. So this is a very important step to calculate a z of z. So what we do is that everywhere we see cosine of omega, we replace it first by z plus z minus 1 divided by 2. We get this one, and then we find the poles and zeros, and then so if zi is a root of that, 1 over zi is also a root of this one. And similarly for the poles. And then we take whatever is inside the unit circle. Remember that if a complex number is inside the unit circle, 1 over z is outside the unit circle, and vice versa. Remember, if I put a circle like that, and if a rabbit is here, if this circle is like a mirror, here is z, so then 1 over z becomes same angle, but it becomes 1 over z. So if this point is close to 0, this 1 over z is close to infinity. So this is how we can do power spectral factorization.